So last time we started chapter 13. So here we're talking more about polynomials. We talked a little bit about polynomials in the last chapter where we did modeling. But here we're going to really take another thorough pass through talking about polynomials. Now, a lot of the ideas that we're going to discuss in here are going to be revisits or small extensions of things we did last year in the Algebra 2 course, which is nice, right? Like, we like seeing the topics that we're already reasonably familiar with, or maybe we don't. I don't know. Some of us might that was a mess. Just give me new stuff. I don't know. But that is what we're doing here. The assignment for Sunday was 1 through 8. Before we get diving into the next set of stuff, does anybody have a question on any of this stuff 1 through 8? Victoria, is that I see your hand? 7? Okay. Yes, sir.
What are the odds we got a home?
Quite high. Yeah, we would mention that later, but since you're asking now. Hi, come on in.
Good morning.
Good morning. Thanks. Oh, hold on. She's not here.
Okay, I'll bring it back.
You're welcome. All right, so Victoria, number 7. I'm going to start by just graphing this in my calculator. So I just started typing in the equation to the y equals spot, because really what I want is the picture. So we've been doing all kinds of crazy graphing recently. So I'm going to check my window real quick. This is up. My window's already set to the standard -10 to +10. The other option you'd have is to click zoom and then pick Z standard. That'll also reformat your window. So here's what I got for a picture. That's good enough because I see the left end is pointing up and the right end is pointing down, which is really all I need. And we are h of x's. So because h of x is a polynomial, I know that this much of it I can fill in immediately. That for polynomials, they have no asymptotes, so all I have is the end behaviors at the left end and the right end. So the left end is represented with the -infinity and the right end with the +infinity. So that much I can copy in immediately without even have to think about anything. Looking at my picture now, the left end was pointing up towards +infinity. So that one should equal +infinity. And the right end was pointing down towards -infinity. So that's that. Is that okay?
But how did you get the X arrow tonight?
So the only things that are ever going to be different are these parts. So that's everything else is the same other than the name of your function or whatever. But like the only parts you really need to fill in are the, where the asymptote's at or where the end behavior is in the case there's no asymptotes in this thing. So it's just the left end. What's the left end doing and what's the right end doing? Is that okay? I feel like I'm just kind of saying nonsense over and over again. It's early. My brain's still like waking up. I felt like I just rolled around all night last night and didn't really sleep. It's becoming a problem. I feel like I haven't had a good night's sleep in like a month. I blame you guys. Okay. Anybody else? Questions from the homework here? Okay. So again, with the limit piece, like this stuff in blue, you write every single time. Like that stuff is always the same. The stuff in green is just going to be the name of whatever the function is that's in the problem. And the stuff in yellow is what you're going to pull from the graph, from looking at the picture or looking at a chart of, a table of data. Could tell you that also. Okay. Anyone else? Questions from 1 through 8 before we jump into the next set of stuffs? Victoria, you're happy? So the notation is just a little bit different than what we used last year, but the same kind of idea when we talk about end behaviors. Yeah.
4, like for the zeros and extremes, is like the 0 just like the highest exponent?
Yeah, so at most, number 4 could have 9 zeros and 8 extrema, 1 less than the highest exponent.
Okay.
Because if you think about it, like if this is my x-axis and I have like 9 things on here, in between each one, I could have like a maximum or minimum, but if I had like 1, 2, 3, 4, 5, 6, 7 zeros, I can only have, right, I had 7 zeros, but I can only get 6 like bends in between them. You know what I mean? So it's always going to be 1 less, the extrema, or the extrema. Okay. All right. So last time, one of the things we talked about was using our calculator to find the x-intercepts or the zeros for these polynomial functions, right? And that's fine, that's effective. But really, going forward, what we'd like to do is develop some algebraic techniques so we can do the same thing by hand as well. So that's really what we're going to be talking about in these coming lessons, is drilling down and developing and building out some of the techniques we'd use to find the zeros for these polynomials by hand. And some of these are ideas that we've done already. So let's say we're just going to run through some examples and review some of these techniques that we developed last year in our Algebra 2 class. So if we're looking to find the zeros for this polynomial function, when I say find the zeros, I mean I'm basically going to be solving this so that it's equal to 0. And the first thing that I'd look for in any one of these solving problems is to see if there's a greatest common factor. So if we look at the polynomial x cubed minus 6x squared minus 8x, do you see a greatest common factor? What do you guys think? Is there something in common with each term of that polynomial? X. Very good. So that's our greatest common factor. Will there always be a greatest common factor? No. In this case, there was, though. So I'll start by factoring off that greatest common factor. Everybody's okay there. Now, once I've pulled that greatest common factor to the front like I've done, it basically just hangs out there until the very end. It's not going to come in packed until we start splitting this thing apart. But right now, it's good where it is. I don't have to worry about it again until the very end. Instead, what I'm going to do is I'm going to look at that part inside the parentheses. And the first thing I look there is the number of terms. Remember from back in Algebra 2, we did something different if there's 2 terms or 3 terms or 4 terms or more than 4. Okay, so how many terms do I have on the polynomial there inside my parentheses? 3. Very good. So if I have 3 terms, what I need to do is, first thing I want to do is check to make sure this is in the quadratic form. Is that in the quadratic form? Definitely is, because the degree of the highest term is twice the degree of the middle term, and then I have a constant term at the end, right? And in fact, this is not only in the quadratic form, this is just a quadratic, since it's degree 2. You guys all remember doing that? Good. So since it's in the quadratic form, we can factor it like a quadratic. There's 2 different ways that we have to use to factor quadratics, depending on whether the leading coefficient is 1 or something else. In this case, what's the leading coefficient on our quadratic? 1. That's good news for us, because that is the one that's the easier way to do it. It's the shortcut. So all we need to do is find 2 numbers that multiply to give us -8. Oops, Mr. Kulik wrote down a bad example. Let's change that to positive. Whoops. +8 and add to give us -6. Anyone can tell us those 2 numbers? Multiply to give us -8, add to give us, +8, and add to give us -6. -4 and -2. And since that leading coefficient is 1, I can go straight to the factored form. Everybody happy there? And now, since each of these factors are linear, they all have degree 1. I have x to the firsts in each factor. I know I'm done with my factoring. So I can apply the 0 product property and just set each one of the factors equal to 0. Keep in mind the 0 product property is very specific. We can only do this if it's equal to 0. If you have a bunch of factored things equal to 5 or something, you can't set them all equal to 5. It doesn't work like that. It's very specific to 0. So if I try to solve 0 equals x, well, that's already done. X minus 2 equals 0, I just add 2 to both sides. And then x minus 4 is equal to 0, I just add 4 to both sides. So my zeros are 0, 2, and 4. Let's do another. What was the first thing we wanted to check? Excellent. Greatest common factor. Juicy one. What is it? X. Okay. What do we do next? We look at the number of terms. In this case, that's 3 terms. It is in the quadratic form. In fact, it is just a quadratic. Before we start factoring this as a quadratic, what do we need to look at?
There's a 1.
Great. The leading coefficient is what we need to check first. In this case, the leading coefficient is 1. So we know it's going to factor the easy way, right, where we can just go straight to our factored form. So to factor this, I need 2 things that multiply to give us positive 9 and add to give us positive 6. 3 and 3. So I have x plus 3 and x plus 3. I then apply my zero product property. So I get x equals 0. Then I get x equals negative 3 as an answer 2 times, right? But when I list my zeros, I just write 0 and negative 3. But what I would say about negative 3 is that I would say that it has multiplicity 2, because that answer occurs 2 times. It counts as 1 0. When we list our zeros, we list it just 1 time. But we're going to write it down or note that it occurs twice by calling it a multiplicity 2. Is everybody okay with that vocabulary? I think that's the same thing we used last year as well. Now, the natural next question would be, can we predict when one of these multiplicities is going to happen, right? It'd be nice to know in advance that that's going to happen. And we can. Yes, of course. So we say that the graph of a polynomial function intersects the x-axis with a bend, then that 0 has a multiplicity of at least 3, or an odd multiplicity of at least 3. And what a bend looks like is the picture I drew below. If it intersects with a bounce, then that 0 has an even multiplicity of at least 2. And I drew a little picture of what a bounce is going to look like. Can one of you guys grab the door for me? Maria, can you put your phone away? Yes. Thanks. Are we okay with this bend, bounce, straight theorem? Again, this is something that we would have talked about last year in our Algebra 3-4 course. So it shouldn't come as too much of a surprise. And this will come in handy once we start talking about trying to find the zeros for these polynomials that aren't easily factorable using purely algebraic methods. Okay, let's do another example like this. First thing I check is a greatest common factor. What's the greatest common factor we see there? Anybody? 2x, yeah. Now remember, when we're doing that factoring, what we're doing is dividing. So that last term becomes a 1. It doesn't disappear. Common mistake I'll see students make. Okay, what now? Yeah, so we notice that it's 3 terms. It's in the quadratic form, but this time the leading coefficient is not 1. So we're going to have to do that longer factoring. So the two numbers need to multiply to give us the first term times the last term, and then add to give us the middle term. What are those two numbers? Multiply to give us 2 and add to give us 3. Two and 1. I didn't hear you, apparently. My apologies if you shouted it out. Okay. So what do I do with that 2 and 1 now? It doesn't take me straight to my factored answer. Instead, what it's going to do is tell me how to break up my 3x. So I'm going to break up that 3x as a 2x plus a 1x. Doesn't matter if you did it in the reverse order, it'll still work out the same. If you did 1x plus 2x, that would be okay also. Yes, sir. Of course. Maybe kick the doorstop in when you go because the door's locked. Thanks, bro. All right. So once we've done that now, we're going to make two groups. Remember that when we make our two groups, we have to have that plus sign in the middle. Is this ringing some bells? Good. If I look at the first group now, is there a greatest common factor? 2x, right? That leaves me with an x plus 1. If I look at the second group, is there a greatest common factor? In this case, I'm going to just put a 1 there. Yeah, there's nothing really in common, but I need to have something there. So if I look now, they have x plus 1s are both in common. So I'll factor that part out. And what's left after I factor that out is the 2x plus 1. Does that ring some bells there for us? Okay. So now that we're all factored up, we can use the zero product property. I divide both sides by 2. I still get x equals 0. Subtract 1 from both sides. Subtract 1 and then divide by 2 to get negative a half. So those are my zeros. Feeling okay? Let's look at a story problem example. So let's say we want to make an open top box. So what do I mean by an open top box? You know, something like this. A box without a top on it, right? Shocking. Sometimes the picture helps, right? The box needs to hold 500 cubic centimeters, aka that's its volume. Did you just hear that from next door? That tomatoes weren't native to Europe. That's a New World plant. What the heck were the Italians doing pre-Columbian exchange? What were they putting on top of their spaghetti? I don't know, right? They probably didn't. They probably weren't eating spaghetti. What was on their pizza? Right? It was a dark time. It's a dark, dark time. Of course. Okay. So we want to make this open top box. It needs to hold 500 cubic centimeters. We're going to make it from a sheet of cardboard that's 26 by 20 centimeters by cutting like a square out of each corner. We want to know what is the side length for that, or what size of squares. All right, so make it a color, huh? So let's draw a picture to kind of start, because, well, any of these problems that are kind of geometric, I think are often helpful to start by drawing a picture. So here's my sheet of cardboard. And it says I'm going to be like cutting a square out of each corner. I guess is that easy to see? I guess that's okay. So I know that a square is the same length on each side. Since the question is asking me for the size of the square, like I know I'm going to make that size X because that's the variable that I'm looking for. That's what I want to find out in the question. I know the squares are all going to be the same size, because if the box is going to be a real box, you want it to have like all the same, side lengths. You don't want it like some goofy, crooked looking box. And we know that the volume here has to be 500 cubic centimeters. All right, here's the big brain buster question for you. Let's go back to our geometry. I know it was a long time ago. How do we find the volume of a box? Length times width times height. Great. So like from here to here is my length. From here, well, let's put it over on that other side. Oops. That's my length. Over here, from here to here is my width. And then like here to here is like my height. Right, because when I fold that side up, after I've cut those corners out, that ends up being the height, right? You guys can kind of see that? Okay, well, I know the height is just X. Well, let's do this first. So I know 500 is going to equal length times width times height. Now, that's not terribly helpful for me, because that equation has three different variables in it. It has L, W, and H. Well, from my picture, I can tell right away that H is just X. Everybody's okay with that? What I'm going to want to do then is I'm going to want to figure out a way to write L and W in terms of X also. So let's look at L first, I guess, since I wrote that down first. This is the length, is this piece right here. How far is that? What did it start off as, that side of the square? I'm sorry, that side of the sheet of cardboard. 26. But we cut something out of it, right? What did we cut out of it? Cut off x on this side and another x on that side. So couldn't I call that just 26 minus x? Or really 26 minus 2x? How about the width? What side, or what was the length of that side of the cardboard before we did any cutting? 20. And then what did we do? Cut off 2 x's. So again, we have 20 minus 2x. Does that look okay? Now I can just set those each equal to 500 and solve, right? No, Mr. Kulik. It's the zero product property. It'd have to be equal to 0 for you to be able to do that. Ah, buggers. So what am I going to have to do? I got to FOIL that all out, right? And get it all on the other side. And then try to redo it. Ugh, Mr. Kulik. Well, it is what it is. I'm going to save you guys the aggravation and do the foiling here. For you. Oops. So there's my foiled out answer. And then we'll just subtract that 500 over. And you know how I would solve this now? Well, I can see there's a greatest common factor of probably 4. I'd have to check on the 92, but I'm sure on the other ones. But that's not so helpful to me because how many terms do I have here? I have 4. And I can look at this pretty easily and see that it's not going to factor by grouping. So what would I do if I can't really factor this by the algebraic means that we've talked about to this point? Well, I'm going to do it on my calculator because I can always do that, right? Particularly since this is asking for the side length of a square, I know it's going to be a real numbered answer. So I don't even have to worry about like an imaginary thing. So I know that my calculator can certainly handle this. So there's that. But before hey, come on now. Oh, I hate you so much sometimes. Well, no, all right, whatever. But before I hit graph on this, I'm going to have to worry about sorting my window out, right? Okay. So x is representing a side length of the box, correct? What do we know about side lengths of boxes? What kind of numbers can those be? Or can't those be? Can't be negative. So the x-men certainly should start at 0, right? What's the biggest possible value for x? What do you guys think? Nope. The biggest possible value for x is 10 y. Look at this side here. If x was any bigger than 10, this side length would end up being negative, right? Because it's 20 minus 2x. Does that make sense? Okay. The y is representing our volume then. Again, volume can't be negative, but I'm going to actually use a negative number here because I'm going to be looking for the x-intercept, and I want to be able to make sure I can see where it's crossing pretty easily. And my volume should go up to, I don't know, 500 or so, I guess. I'm just going to start with that, and if I have to adjust it, maybe I adjust it. But I know 500 is a reasonable volume for this situation, since that's the volume that we're looking for. So let's go ahead and graph. Whoop! Well, there we go. I see two x-intercepts. What does that tell me? There's two answers. That's fine. Not a big deal. So to find those x-intercepts, I'm press second, and then the trace button. And which command do I use to find x-intercepts or zeros for my function? The zero command. So here it's asking for left bound, right bound, and guess. So I'll find the furthest left one first. So there I know that I'm below the x-axis because my y coordinate is negative. I'll press enter. I'll move to the right a little bit. I'm above the x-axis, so I can see my y is positive. Press enter for guess. So I get 196 as one value for x. Let's find that other one now. Second trace, zero command. Left bound, enter. Right bound, enter, guess. And I get 367-ish. So I have two answers. That's okay. What do you guys think on that? Hardest part was probably getting it set up, right? Drawing the picture and figuring things out from there. But after you did that, it wasn't too much to do. And again, draw the picture. It helps a lot. Anytime there's like a geometric type situation like that where you can look at a picture, Woofarowski, that helps me, right? All right. We're going to start in section 3 here today, but we won't finish it. We're just going to stick our toe in here a little bit. So in section 13.3, we're going to start working out some more methods of finding these zeros that aren't relying on the same kind of factoring we've been using. So what I want to go back to is remembering long division way back in our yesteryear. So let's say we had something like 94 divided by 16. How did we set something like this up? Go back to your elementary or middle school when you last did long division. Okay, 16 goes on the outside of the thingy. And then what? The 94 goes underneath the thingy. That's good. And then what do we do? How many times does 16 go into 96 without going over, right? Now, it doesn't have to be exact. You could take more than one step to do this, but usually we try to make it exact. So 16 times 5 is 80. And then 16 times 6 is 96. So I guess it's 5, right? So I did 16 times 5, and I write it underneath. Then what do? Subtract down. And then that is like our remainder, right? So we'd say 94 divided by 16 is 5 and 14/16. So just as some vocab here, this is the 94 is the dividend, 16 is the divisor, 5 is the quotient, 14 was the remainder, and 16 down here is the divisor once again. So just a little piece of vocab reminder, the little parts of the division problem. So we can say the same thing now in terms of polynomials. We have some f of x divided by a d of x. That's going to give me a quotient q of x plus the remainder r of x over the divisor d of x. So it's really the same kind of setup as the long division problem. But remember again that division and fractions are really the same thing. So often, instead of writing it as polynomial divided by polynomial, we often will write it as a fraction. That's still the same thing, right? Okay, so here's our polynomial division problem. Again, was this something we did last year? Yup. Okay, how do we set this up? Same way we did the long division problem. So what part goes on the outside of the thingy? Okay. And what part goes underneath the thingy? The top part. Now, if I look at the top part, I see I have x cubes, I have x squareds, I have x's, then I have constants. I didn't miss any terms along the way there. But if I look at the bottom, I have x squareds, no x's, and then constants. What I find is quite helpful is to include a 0x there. So when I do this problem, everything continues to line up for me automatically. I don't have to worry specifically about like, oh, did I put that under the right thing to do my adding or subtracting? If I include those extra pieces, put in the zeros for mixed, if I skip a term, that keeps everything lining up nicely and doesn't cause a lot of problems for me. That's a nice tip. Do you need to do that? No, if you're paying attention, it'll be fine if you don't, but like, boy, I think it just makes your life easier. I would do it. I do it as the math teacher, you know. Anyways, all right, let's start now. So what do? We start by asking ourselves, what times x squared gives us 2x cubed? Now, when we do this, we only care about the leading coefficient. At any point in this, we never care about anything but the leading coefficients. So what times x squared gives me 2x cubed? 2x. Everybody agree with that? Okay. So then I multiply that 2x to the entire thing and write it underneath. So far, so good? Now what do we do now that we've written it underneath? We have to subtract down. Now this is a place where frequently students make a mistake, because when we're subtracting the entire polynomial. So really we have to make sure we're distributing that negative through. So after I've written it as like the negative or the subtraction symbol out front, I'm going to distribute the negative through and really think about it as like an addition problem. Because boy, it's easy to like goof up that you're subtracting each one of those three terms. Probably the single most common mistake I see students make in this, doing this, is goofing up that negatives when they're trying to combine their terms here. So when I add down now 2x cubed plus a negative 2x cubed, those just cancel out. Negative 4x squared plus a negative 0x squared, well, just negative 4x squared. And then I have 5x plus 6x, that's 11x. And I bring my next term down. So then I'm going to ask myself, what times x squared gives me my new leading coefficient, negative 4x squared? Negative 4. So I do that. Multiply it to each piece. So that gives me negative 4x squared minus 0x plus 12. And then we'll subtract down. But instead of thinking about this as subtraction, I'm going to distribute the negative through and turn it into an addition problem. Is that okay? Negative 4x squared plus 4x squared is nada. 11x plus 0x is 11x. And then 1 plus negative 12 is negative 11x. That's now going to be my remainder. I can tell that's the remainder because the degree of this is less than the degree of the leading coefficient on my divisor. That's automatically going to tell me that I'm done. So the answer, the way that I would write this, so I'd have my original problem here that we're asked to do, is equal then to the quotient 2x minus 4 plus my remainder over my divisor. Does that look familiar from last year? We definitely did polynomial long division last year. We'll do it again here for a little bit. There is a shortcut version to this that we'll talk about here in a little bit. But this is where I wanted to stop here today. So if I look at the problem set, you guys can now do 9 through 12. And can do 15 through 19. That looks good. 9 through 12, 15 through 19. Yes. You're welcome. So again, wanted to point out to you guys that the odds are pretty fair that you'll see the homework quiz for this chapter on Wednesday. You'd be looking at just really section 1 questions. So you definitely want to make sure you're comfortable like using your calculator to find extremas and zeros and using that limit notation to describe end behaviors, and should be able to competently use our calculator. That's going to be most of what I'll ask you to do. Correct. Yep. Does everybody feel okay there? All right. Hold on, guys. Again, I would want to point out that many of us are missing a lot of homework assignments. Okay, thank you. I haven't done that ever. Some of us haven't done a homework assignment this semester yet. If you're in that boat, please, for the love of God, let's try to pass the semester. Let's get some stuff done. Let's build ourselves some cushion. Has Mr. Kulik been like super generous and flexible about late things all year? Yeah. Like don't wait till the very end, because Mr. Kulik becomes like pretty whiny about getting 100 homework assignments in the last week of school, but is like pretty okay with getting like a couple of extra ones a week. Like with a couple virtual days going on here, let's try to get some stuff done this week, okay?